Welcome. Thank you all for taking the time to attend this webinar, Dispatch Optimization of Floating PV Hydro Hybrid Plants. Today we will hear a recap of the last webinar and an overview of the AquaPV toolkit from INL Clean Energy researcher Juan Gallego-Calderon. And we'll also hear from INL Power System Research Engineer Mucun Sun about optimization strategies for hybrid AquaPV systems at hydropower facilities. During the webinar, we will ask a couple of interactive questions, and you'll have an instruction page on how to submit those answers to those questions. There will be a link in the chat, and there will also be a QR code later on. And we are always open to questions, so if you have any throughout the presentation, please feel free to send those in through the chat, and we'll come back to those during the last 15 minutes in a Q&A portion. We'll also be unmuting mics if you want to ask the question verbally. You'll just have to raise your hand so we can manually unmute your mic. And then at the end of the webinar, we'll also be sending in the chat a link to a Qualtrics form to collect feedback that you may have. So if you have a moment, please give us that feedback. We'd love to hear it. And with that, Mucun, I'll go ahead and hand it over to you.
All right. Thank you, Katie. So let me start. Good morning and good afternoon, everyone. Thank you for having me here today. And also thank you, Katie, for the introduction. Again, my name is Mucun Sun, and currently I'm a power system research engineer at INL. Today, I will be discussing whether hybridizing floating photovoltaic floating PV systems with hydro and battery storage can make floating PV more feasible in the long run. So this is a second webinar in our series on the floating PV project. About a month ago, my colleague Juan here and Aaron Yuan from National Renewable Energy Laboratory, NREL, have presented the first webinar, which covered our floating PV AquaPV toolkit. If you missed the first webinar, don't worry. My colleague Juan will provide a recap later, and we will share a QR code so that you can explore the AquaPV toolkit yourself. Here is our project team. I would like to extend my gratitude to our project team for their excellent work in making this AquaPV toolkit a reality. It is a wonderful team, including national labs, INL, and NREL, university, Oregon State University, and the industry, including Nori Energy, and DNV, and Cat Creek, and Eagle Creek, those industries with different kinds of expertise. I also want to thank Water Power Technology Office, WPTO, and the Solar Energy Technology Office, SETO, for providing the funding to support this wonderful research. Next. All right. Before jumping into the slides, I want to have an open-ended warm-up question for everyone here in the webinar, and also it gives more time for people joining this webinar. So the first question will be, what is the first energy source or technology that comes to your mind to complement floating solar power, floating solar development? Yeah, you can put your answer in by using the link provided, or just scan the QR code here. And then I will give 1 or 2 minutes for you to input the answer. After that, we can take a look at how everyone think about floating solar development at a first glance comes to their mind. Katie will put the link in the chat, I believe.
Hey, Katie, can you scroll? Oh, yeah. Oops.
Nice, nice. I saw so many people put pump hydro, dam, and energy storage battery here. Cool. Thank you. more time. Katie, could you help like scroll down and up so everyone can see the answer from other folks? Thank you. Okay, one more minute. All right. Katie, could you scroll down and up so everyone can see those responses? All right. I think we got a couple of responses, around like 8 or 9 responses. Most of them are like energy storage and also hydro. Those are so probably those two very common things when it comes to floating PV. And you think like hydro and battery can complement with them. Okay, since this is an open-ended question, I will call back at the end of this presentation. Okay. Next slide. Okay. So here is our today's agenda. First, my colleague Juan will provide a refresh on the floating PV project overview. Following that, I will then discuss hybrid energy systems, including their definition, different topologies, and the benefit of such hybrid systems. Next, I will cover energy dispatch optimization, starting with a short-term dispatch optimization, and then moving on the motivation behind our work, long-term energy dispatch optimization. I will then explain in detail how we define the problem, how this long-term optimization can help assess the feasibility of hybridizing floating PV with hydro and battery storage in the long run, using a case study as an example. Finally, I will introduce our ongoing work, take questions, and close our today's webinar. Now, I will hand over the slides to my colleague Juan for the project overview. Here we go, Juan.
Thanks, Mucun and Katie. Hi, everyone. For those of you who don't know me, my name is Juan Gallego-Calderon. I'm the principal investigator of this project, and I gave a webinar about a month ago about our tool, AquaPV. But first, maybe I can just talk at a high level what the scope of the project is. So this is funded by the Solar Energy Technology Office and the Water Power Technology Office. So the idea is that we wanted to see what opportunities there are for development of floating solar and U.S. reservoirs. That includes reservoirs regulated by FERC and those regulated and owned by the Bureau of Reclamation and the Army Corps of Engineers. So far, there has been several floating solar projects in the U.S., but those were limited mostly to ponds or man-made water bodies that have a different type of regulation or owner structure. So the interest of this project is to see at a more utility scale what can be done in floating solar. So we have these 4 sort of pillars of analysis. First, we have the resource assessment, where my colleague Evan Rosenlieb and together with Mary Rivers and Aaron Levine at NREL, they did a technical potential, and we will have a webinar coming up in December about that basically says, hey, this is the maximum technical potential on each of these reservoirs that, based on resources and trends regarding to the site, you could install. Then we have a techno-economic analysis tool that is tailored to floating solar, and that's where AquaPV came into play, the web app that some of you are familiar with, where we're collaborated with Noria and DMV on developing a easy to use tool that tells you how much it could cost you to build a certain floating PV between 1 megawatt and 100 megawatts. The data behind that tool comes from real life projects. And we have, it's open source as well. So what we basically tell you with that is how much is it going to cost you and what is the levelized cost of energy, return on investment, etc. My colleague Aaron also published a report on the regulatory assessment, like what are the opportunities for deployment and licensing of this type of projects in the U.S. reservoirs, and we talked about it in the previous webinar. But if you're curious, if this is new to you, we could drop the link in the chat as well. And then we also included the environmental aspect. That one is a bit tricky because it's based on modeling, since we don't have large-scale floating solar in multiple locations across the US. So we use some existing reservoir models to basically see what changes would put shading on top of the reservoir would have in certain metrics like water temperature, dissolved oxygen, etc. So the project tries to cover all of these, and a lot of it is condensed in the AquaPV tool. And basically, our main deliverables were the AquaPV tool to do the TEA analysis and environmental and present the results, the regulatory report that I just talked about, and then the high fidelity resource assessment. Next slide. So who is this tool or the project designed for? So we are not targeting one set of stakeholders, but rather we are going a little bit more broad. And because we, the level of detail that we're putting in the tool is kind of hard to target just one category of stakeholders. So we have about 5 stakeholders, and here we have a description on how they can use the tool. So, for example, solar energy developers that are interested in getting into the FPV space or are already in it, but they are interested in going to more utility scale in the US reservoirs, they could use this tool to identify potential sites and do a pre-feasibility economic assessment and go from there. Hydro developers are also very important because as dams get retrofitted, like non-power dams get retrofitted, or existing dams get upgrades, or there is exchange of ownership or who's running them, they could use our tool to see if there is some co-benefits to developing also with floating solar to support their development efforts on hydropower. NGOs can also use it to look at where these plants could be located and seeing the potential benefits or impacts either to communities or the environment. And then utilities or hydropower operators who maybe are not involved in anything regarding solar, but they're kind of curious, they could use the tool to say, hey, we have space in this dam, between our dam and the setbacks, and how much can we get extra for but utilizing that space. And then same with asset owners, just basically identifying what are the opportunities that are out there for developing a floating solar. Next slide, please. So yeah, just a little plug to our tool, AquaPV. You can scan the QR code, but the link is pretty simple. It's aquapv.inl.gov. And you can there's 5 things that I mentioned before. You can just go in and go over the tabs and explore. And I might just stop there and let Mucun take over again to talk about his work. Thanks, everyone.
Yeah, thank you, Juan. Thank you, Juan, for the introduction and the overview of the AquaPV toolkit. Then let's take a look at more technical stuff. First, let's take a look at the hybrid energy system. When it comes to like hybrid energy system, there is like an increasing interest in hybridizing generation resources with battery to enhance the flexibility and value of the prime energy resource. And also the value proposition of hybridization are like particularly significant for variable renewable energy resources, such as like wind and solar. Consequently, this type of like hybrid system has been like most studied and deployed in like real world. From figure, as you can see, it summarizes like different topologies of hybrid energy system. This figure is still from a paper from my colleague Juan, and there are three topologies of multi-energy system. First, it's like a co-located integrated hybrid system where like the primary energy system and battery storage operation is coordinated and like share a common point of interconnection. And as you can see from left-hand side, the first two figures, co-located integrated and co-located independent. Different from the co-located integrated hybrid system, a co-located independent system mainly have the primary energy resource and the battery operating independently of each other while sharing like a common point of interconnection. Then other than that, we have like a virtual power plant. A virtual power plants, those we call VPP, have like a separate point of interconnection, as you can see, for the primary energy resources and the battery, but they have like a coordinated operation between them. For different topology of hybrid energy system, they have different benefits. For example, for a co-located system, it can decrease the cost through shared balance of system costs and interconnection charges as well. And then more details about the benefits from hybrid system will be talked next time. Go next. Then let's take a look at the benefits of like pairing floating PV with hydropower and battery. In our warm-up questionnaire, many people respond like, what's the first, at the first glance, what do you think is the best technology or energy technology can be paired with floating solar? People give answer of hydro and battery. Yes, you're right. Because floating PV is floated on the water body, such as a like lake, river, or even the sea. So but naturally, it's very good to pair that with hydropower resources. And also, as I mentioned in the previous slides, adding battery to making it like a hybrid system can provide some benefits. First, let's take a look at the grid benefits. We know renewable energy such as like PV, their like outputs are pretty capricious and vary. Sun is not always shining, so we'll not always have solar power generated. They only generated during days, but not at nights. However, with a stable output from hydropower, the energy output can be smoothed. Also, pairing floating solar with hydropower and battery can provide like a higher generation capacity as well. Hybridizing these assets with batteries can enhance the value of the produced energy by allowing them to shift the production to higher price hours. Those called as like load shifting. And also they can provide ancillary services and black stars as well. Let's dive a little bit into the load shifting. For example, some market participants strategies originally developed like for solar plants could be adopted to like run-off river hydropower to mitigate the effect of like inflow uncertainty. And this market participation of variable renewable energy resources like solar power plants can result in like penalties due to the forecasting errors and the dynamic nature of real-time prices, like compared to day-ahead prices. Because you participate in a day-ahead market and you have like a forecast, and then if there's some mismatch, definitely you pay the cost. There's some penalty. To avoid this, multiple floating PV producers are being like coordinated with battery storage facilities to form like a virtual power plant to maximize profit using optimization approach. Then let's talk about some like non-grid benefits. First, pairing FPV with hydropower and battery can reduce the total maintenance cost. We know that those hydro units have had experienced more wear and fatigue and will experience more frequent operation shutdowns for maintenance. By applying the hybridization control strategy in a hydro hybrid unit pairing with floating solar and also battery, that can rapidly changing signal fed to your energy storage system, and we can have a slow varying dispatch signal fed into the hydro unit to reduce the wear and tear. So based on some research, it has been shown that compared to hydro hybrid case with solar and battery, the damage breakdown for this system can reduce by almost 30%. And the percentage damage reduction will increase as the storage size increase. That means the bigger size of battery, and the damage reduction will be more significant. And also the economic benefits from damage reduction can be as high as around 9.5 million when replacement cost is about 1 to 2 million per megawatt. Not next one second. And there is another benefit I haven't talked about, including non-grid benefits like aquatic ecology, and also incentives like production tax credits, including ITC and PTC. It is also to mention that there are also some carbon credits can be gathered by pairing FPV with hydropower and battery. Those carbon credits are permits that allow entities to emit a certain amount of greenhouse gases, and they create incentives to decarbonize faster than a fully deregulated market would have. Next slide. All right. After we take a look at those so many benefits brought by pairing floating PV with hydropower and battery to make it a bigger hybrid system, let's take a look at the energy dispatch optimization. First, in terms of horizon, it has short-term energy dispatch optimization and long-term dispatch optimization. So first, let's take a look at short-term dispatch optimization for hybrid plants. It has different objectives. First, our dispatch optimization can make our site, the hybrid plant, have higher revenue. So we put a revenue as objective function. Also, if you want to improve your green gas emission to make a lower green gas emission, you can put that as an objective as well. Also, we can change the objective function to provide better ancillary services and also providing some environmental needs. For example, for recreation purpose, you need to have a win-win solution between the flow level and the revenue you get from the system. So you need to follow some flow constraints for recreation purpose like boating, and also you need to follow some flood constraints to avoid flood. And there are some other fishing and agriculture criterions, environmental needs you need to follow. So those are different objectives. Let's take a look at the right-hand side figure. So this is a short-term dispatch optimization and also battery sizing optimization flowchart grabbed from a journal paper from my colleague Yin Chen and Bing Hui. So from this flowchart, as you can see, hydropower generation and market price and energy storage devices have a assumption of the possible assumption of the sizing of battery as an input. For the hydropower generation and electricity market price, there goes through a two-step optimization. One is day-ahead optimization, and another one is real-time optimization. In day-ahead optimization, you need to provide the short-term forecast for day-ahead short-term forecast for electricity price and also the possible hydropower generation. So, and then when it comes to in day ahead, you perform a optimization and also get the optimized battery size. Then here comes to the real time. you need to like fill the gap of the mismatch between your forecast in day ahead and the real time. So say, for example, if you like forecast 100 megawatts and then you sign a contract in day ahead, but then you overestimate your production. So then you probably need to like purchase, you only generate like 90 megawatts, then probably you need to purchase another 10 megawatts from market in real time. There's some penalty. So those how the mechanism work in this short-term dispatch optimization. And also most of the inputs as forecast inputs for price and hydropower generation, they're deterministic. That means that they only provide like a single value at each time step, including the price forecast and the renewable energy forecast. Next, let's take a look at, okay. Next, let's take a look at we just talked about like the short-term dispatch optimization, and there are tons of literature on website about short-term dispatch optimization regarding different objectives. Then we switch gear here to the research we want to do, the long-term dispatch optimization. First, let's talk about some like our motivation. Why long-term dispatch optimization for hybrid plants? The most straightforward answer comes to your mind. Maybe it can provide like an intelligent operation for a hybrid system, and it can provide in higher revenue in selling electricity. Maybe after optimization, it can provide better ancillary services. Also, probably you can, after optimization, as I mentioned in the previous slides, it can provide a lower maintenance cost by hybridizing the system. For example, if we take a look at the right-hand side figure, so this is a research of cost reduction from optimized operation in a hybrid offshore wind, hydrogen, and battery system. From the figure, as we can see, let's take a look at the top two figures in gray and in red. So after optimization, the optimized operation can reduce the O&M cost, the operation and the maintenance cost by like around 20 million. And it can reduce the total cost as well. Total cost is like right-hand side, the red curve. And also, if we take a look at the lower two plots, it can reduce the LCOH and LCOE as well for the system after the intelligence optimization operation. So, however, now after looking at this, it comes to a question. Most of existing techno-economic assessments for the hybrid energy system, they either simply calculate the revenue by multiply generation to energy price without considering any optimization for simplicity purpose. Sometimes they also didn't consider like the long-term dynamics in the electricity market. Also, in the electricity market change and also renewable energy generation change when it comes to the forecast. They simply repeat the current year value or either just the next year forecast for like next 30 years or next 90 years as a long-term forecast. Thus, it can't reflect the true value of the hybrid system. That means the traditional techno-economic analysis of hybrid plants often underestimates the economic advantages of long-term optimization, and also the benefits derived from projecting long-term market dynamic may be underestimated. Next slide, please. So to solve this problem, we try to propose like a long-term dispatch optimization framework to assist our hybrid floating PV, battery, and hydro system to make it like a more realistic techno-economic assessment. Also, it can provide our audience, our possible potential users, with a like more realistic understanding how much the gap can be and how much it may take to make our system break even. How much is our payback period calculated realistic or not? So these are the questions we try to answer. So on the right-hand side, here is the overall flowchart of this dispatch optimization framework. In this work, we plan to generate like long-term electricity price forecast, hydropower forecast, and solar floating PV generate solar generation forecast. And also, when we generate this long-term forecast, we try to consider the market dynamic and also the weather change to make it more realistic. Then these inputs will be fed into a defined long-term dispatch optimization model. I will talk about this model and the framework later, and to show its realistic value. And then after that, this information I mentioned above will be used together with our AquaPV toolkit to perform the TEA and give user recommendations and suggestions. So here, as you can see, our problem definition, our goal is to maximize the long-term profit for the hybrid system. And the problem will be subject to 3 constraints, including battery constraints, flow constraints, and PV and power system constraints. Then after that, the CAPEX means are like capital expenditures, OPEX, the operating expenses, and the battery costs will be estimated and adding that into the objective function. On the bottom, this is our objective function. We are trying to maximize the long-term profit of the whole hybrid system. So the first term, 3 terms are the battery cost, the OPEX of the whole system, and the CAPEX of the whole system. And then the right-hand side, this is in the brackets. This is a total revenue over its life period. So this, I can go into more details in the next slides. All right, let's take a look at revenue first. So for the revenue, RT is like the flow, and then we convert the flow to hydropower using a tool I will introduce later, and then the P, and then PTS this is a solar power generation. Sorry, I typed it twice here. And then PT minus and PT plus is the like charging and discharge of battery at time t. And then LIT, this is electricity price at time t. And this II, this is like incentive, such as like a PTC and ITC at year I. So across this life term, adding this, all of this revenue selling electricity, this is and its incentives, either state incentives or federal incentives, those are the total revenue. And then if we considering minus the battery cost, OPEX and CAPEX from this revenue, that would be our total profit. So our objective is to maximize this total profit. Here, as you can see from the left-hand side, for the system like OPEX and CAPEX for the floating PV, we can estimate that from our AquaPV toolkit. So this is this figure, left-hand side figure, gives like a breakdown of each cost of OPEX and CAPEX. And for the battery total cost, we are grabbing that from a Unreal utility scale battery storage research. We grab like the CAPEX and the utility OPEX from Unreal report. Then let's take a look at the 3 set of constraints. First, the battery constraints. It have like a charging and discharging limit, and also it has like a state of charge, minimum and maximum state of charge, and it has like an initial value of the state of charge. So we set that as like 0.03. And then for the flow constraint, it definitely has a minimum and maximum flow rate, and it needs to follow the water balance equation. And there are some spill limits and ramp limits as well. Other than that, we have a PV system constraints. So the solar generation can't be bigger than its capacity. And also there, because those systems are connected to a transmission line. So there are transmission limits as well. So for our case, the floating PV capacity is like 30 megawatt DC, and the battery size we assume here is like 5 megawatts, and the hydro is 40 megawatts, and transmission limits is 45 megawatts here. Next slides. First, after I introduce like the objective function and the problem definition, let's take a look at our inputs. As I mentioned at the beginning, we try to make our inputs realistic. We need to generate 3 forecasts. One is long-term hydropower and floating PV generation forecast. So first, may I ask why the renewable energy forecasting needed? From like power system objective, because power system is like a cyber physical system that need to supply electricity power to consumers and reliable economically. And so, and our power system designed to like operate within a very narrow frequency around like 60 hertz. So maintaining the system frequency is one of the fundamental stuff. We need to get like supply and demand meet. That's the importance of forecasting. But here, I won't talk too much on that. I will just take out how we perform this long-term forecasting. So the key drivers of renewable energy generation for hydro, including like the flow and also the weather information, where we can get like the future flow projection for the United States for the next like long term. We are grabbing that from a CMIP-based multimodal stream flow projection over the continental US. I think this is a report from Oak Ridge National Lab. And also for the weather information by different balancing authorities, we are gathering that from PNL's weather research portal. They provide like the hourly meteorology projection by different balancing authority. That's sweet. It is super useful in this project. And also for the floating PV, we are gathering the weather information at GHI, DNI, and the DHI. And after we get the flow forecast and the irradiance forecast, how can we transfer that to energy? So at INL, we have a hydro generated tool, and the link is provided. The GitHub link of this tool is provided below. So if we provide like the heads of the site and also the turbine type, it can convert the flow to hydropower. Similarly, transferring irradiance to power, we are using like a Homer to convert the floating PV irradiance to power. And on the right-hand side, as you can see, here are some examples for long-term flow forecast and irradiance forecast. It's very capricious over a long time and very hard to forecast. Luckily, we have the resource from Oak Ridge National Lab and PNL National Lab give us this kind of weather forecast and flow forecast. Next slide. Then, after we talk about like renewable energy generation forecast, let's take a look at a more difficult one, the long-term electricity price forecasting. For electricity price, the key drivers of long-term electricity price are like load, supply, weather, fuel price, and also policies. There are so many things you need to take into account to provide like a long-term price forecast. Because of the nature of long-term forecasting, so it should be probabilistic, because deterministic forecasting cannot represent the long-term uncertainties, reflect that in the forecast. On the right-hand side of the figure, as you can see, is a monthly average wholesale electricity price at selected balancing authorities. This is from a report provided by EIA. As you can see, the price really differs by different balancing authorities. That varies a lot. That also shows the importance of mapping this projection by balancing authority in our techno-economic assessment to make it more realistic. We can't simply just using an average price or just doing a simple mapping or just assume should make an assumption of like the same price over the next long term. And on the right bottom figure, here is an example of long-term electricity price projection at the selected node from the Duke Energy balancing area. In this study, in the later slides, I think I only show the determinate forecast. We haven't shown the probability forecast yet, but later in our upcoming journal paper, we will show the results for probability forecast. Those probability forecasts are in the formats of confidence intervals, scenarios, and quantiles. Next slides, please. Here are some like our case study sites and our like forecasting results. Our case study site is at like Tuckerton Reservoir. It's near like Charlotte. So it belongs to like Duke Energy Balancing Authority. And on the right-hand side, as you can see, using the weather information from PNL weather portal and the long-term load simulation from PNL's TEL Python package, and using the hydro inflow projection by Oak Ridge National Lab, we can generate the forecast like this. As you can see, if you take a look at the middle one, the LMP price, we forecast like the next 30 years. And there is a huge variation year by year because it's heavily weather-driven, load-driven, and demand-driven. In this case, in this study, because we haven't got information for the incentives and fuel price, so we haven't used those as features in the long-term projection. Next slide, please. All right, let's take a look at our like long-term optimization results. For the dispatch optimization, we are performing like we consider 3 scenarios to show the benefits of dispatch optimization, and also want to show the benefits of pairing battery and hydro with floating solar. So we have 3 cases. One is hydro only. Another one is hydro plus battery. So this is like a 5 megawatt battery with 4-hour like duration, and also hydro plus floating PV and also battery. And the detailed parameter of each system are listed below. So let's take a look at it first. Let's take a look at the results. So for the results, we plot like the generation of each component, hydro, battery, PIP, and PV over like a selected period. So this is like a 3-day period, 72 hours. And the reason why we selected this period is that if you take a look at figure 2 and figure 3, the green curve is like the state of charge of battery. Over these 72 hours, there are very frequent change in the battery charging and discharging state of charge. And we plot that over price. From left-hand side figure, we can see when the electricity price is low, and the system started to like purchasing like power from grid. Because this one is like a runoff river, but we still consider there is like a small reservoir storage. And then take a look at middle one. When the price is low, started purchasing power from grid as well. And when the price is high, it started to like use stored energy in the battery, and it becomes like more obvious if you take a look at the right-hand side figure when we have both floating PV and battery, especially when the PV not generating any power during night. Here, if you see the like gray area, the hydro and the battery started to power. Next slide, please. All right. In the previous slides, we show the results of dispatch optimization over a 5 megawatt battery. We want to understand like which battery size is the most optimal battery size. So what we do is we perform a sensitivity analysis of our dispatch optimization over different battery size. With from no battery, 0 megawatt, to 1 megawatt, 2 megawatt, 3 megawatt, till 5 megawatt. In the plot here, I only show the difference of 5 megawatt and 1 megawatt. And then in the next slides, I will show like more details. So from these slides, as you can see, the difference is pretty obvious. So for the 5 megawatt battery, when the electricity price is high, and it will like use more battery. When the electricity price is low, it will save more energy in the battery, and also use more battery when use more energy from battery when the electricity price is high. As you can see the difference from left hand side and right hand, 5 megawatt and 1 megawatt. Next slides, let's take a look at a more detailed comparison. Okay, the previous slide is just hydro plus battery, and I think for this slide it will be more obvious having floating PV and battery together. Similarly, with a bit bigger battery, it can save more energy, and then it can generate and then can provide more energy during like high electricity price hours. Let's go to next slide. Here, let's take a look at the summary of a battery size versus its profit. Still remember the objective function. The profit is the revenue and minus all of those costs, including the capex, opex, and the battery cost. So as you can see, we use a battery cost from Unreal report listed in the right-hand side table. And as you can see from the left-hand side two figure, for the hybrid system, hydro plus battery itself, and hydro plus FPV and battery itself, as battery size increase and the total profit decrease. Why? Because the battery is super expensive, especially for like especially when the battery size increase. But now adding the floating PV have less profit than has less profit. It's like, as you can see, it's 1.1 and have hydro and batteries over 1.15. Why? Because having the floating solar, it add like its capex, solar capex and opex. So it needs like a long term to get it paid back. Then let's take a look at the revenue comparison. That's more straightforward. So on the right hand side, the revenue comparison, hydro PV and plus battery has like more revenue than just a hydro plus battery. That shows the importance in pairing hydro and battery with the floating PV. And then more interesting, let's take a look at the profit comparison between no optimization and profit with optimization. The red bar is like the profit with optimization. As you can see, after long-term dispatch optimization, the average total profit can be improved by like up to 24%. That's huge. So definitely that shows that if we just use a profit calculation without any optimization, that will heavily underestimate of the economic benefits of the full system when we perform technical economic assessment. Also, based on the calculation, if the battery cost continuing decrease by like around 44% over the next 30 years, considered like a lifetime period, and this hybrid system will be more economical. Next slide, please. Here's all of our work. Let's talk about some work in progress. Next. So the work in progress is we want to analyze like the complementarity analysis of existing hydropower assets and potential FPV. This is very important because we can, by doing this complementarity analysis, we can identify the high value sites based on the complementarity of the hydropower and the PV resources. How we do that? So there are two metrics to define the complementarity. One is a stability index, and another one is a Pearson correlation. If the many of you may heard about like Pearson correlation. So when the correlation is high, that means like it's less complement to each other. When the correlation is low, that means it's complement to each other. And also, we want to consider in the sensitivities to locate on the overall project cost, capex and opex, and also the financial outlook throughout the life of the project. So for the complementarity analysis, we select around like 40 sites with the potential floating solar and the powered existing hydro assets from the Oak Ridge database and from the US GS gauge data in the US. That's the slides, please. So similarly for the complementarity analysis, on the right-hand side, as you can see, first we identify the co-location of potential FPV and the existing hydro assets from Oak Ridge report. We have like around 40 sites here. The white dot is a floating PV location, and the pink dot is existing hydro assets location. Similarly, to estimate the complementary analysis, we use a time series of historical inputs that includes a historical hydro generation and the historical solar generation, and we calculate this figure is this is like a stability index of those 40 sites. So this is still ongoing work. So I just show some very rough results here. Then next slides. All right, here comes to like another question. Because time limit, I will just give you 1 or 2 minutes here. So after you hear about this presentation, what is your greatest concern about floating solar feasibility? Give you 1 minute to put the answer here. Wake up, folks, more response. Okay, I see some response here. Permitting, operation and maintenance. PV doesn't increase profit. True. Water, environmental concerns, water contamination, leaching. Cool. Startup cost. True. Damage to floating solar. Give 1 more minute. Cost competition, yeah, is land-based solar. All right. I think I will, stop here, and then I will send the answers of this questionnaire to everyone, and we will use this as record. Here, I want to introduce our next webinar in the series. We will have a floating PV technical resource assessment and regulatory pathways on December 5th, 12 p.m. Mountain Time, same time as this webinar. And the objective in this section, we will explore like the technical resource potential at federal controlled reservoirs and associate regulatory pathways for obtaining floating PV projects approval from federal agencies. I think this will address some of the questions you answered in the questionnaire, like those licensing, permitting, and those regulatory questions. All right, that's all of my today's webinar presentation. Happy to take questions here. Thank you, everyone.
Just a reminder, we can take questions via mic if you have them. I did not see any questions come in through the chat, Mucun, so it's just if anyone has questions they'd like to ask, if you raise your hand, we can unmute you. Otherwise, I think that's the end. Yes, there will be a recording available of this presentation and the previous presentation as well, and those are available on YouTube. As soon as this is finished, I'll make sure to get this recording uploaded and send out that link to everyone's emails that you use to register for this event.
I'm gonna drop my email and also Mukun's email in the chat. If you have further questions, want to dive into the technical details, please shoot us a message. It was very helpful to connect with some of you last time via email and to, have a broader discussion on where we can help if we miss something. And looks like Joseph Thurl has a question.
Hi, Joseph.
Hey, Kate.
Hi. I was wondering if there are opportunities for specifically tribes to develop floating solar. I know Nimifu Energy is doing a lot of development in the solar power with the Nez Perce tribe and Coeur d'Alene tribe.
I think that's a really good question. I think, as I mentioned, right now in our AquaPV tool, we have the location for like the floating PV sites across the United States, managing by different locations, entities, correct? And then if you can provide like longitude and longitude of that tribe like location, we can match if there are some like existing like floating PV sites there, or if there are some like existing hydro assets there, and then we can start from there using those existing hydro information, and we can go through our AquaPV tool and go through our ongoing complementarity analysis to assess if it's feasible to add feasible or beneficial to add a floating PV there, and if yes, what's the size of the floating PV, and we can provide the sensitivity analysis if we want to add a battery or not. So yeah, we can do that as long as you can provide like the tribal information, because right now in our work we have because I mentioned at the beginning, we have those floating PV sites categorized by different balancing authorities. So we know the electricity price across the United States at all of those FPV locations, and we have all the long-term electricity price forecast for those locations. So as long as you provide the location information and some detailed information, and we can like start from there to do the estimation and evaluation. Good question.
I don't know, Joseph, if you're familiar with the investment tax credits from the Inflation Reduction Act bill that was passed recently. So especially for tribes, I think you can get an extra credit as well. So I think it could go up to 50%, but I will encourage you to look into that in terms of like incentives for this type of deployments within tribes territory.
Great, thank you.
You're welcome.
Yeah, the lower Snake River dams are within the Nez Perce Aboriginal Territory, and then the Post Falls Dam on the Spokane River would be within the Coeur d'Alene Tribe's Aboriginal Territory.
Yeah, I mean, I would love to learn more. So please shoot us an email and we can connect. And however we can help you, we'll be happy to do that. So yeah, feel free to email us. I just posted both of our emails in the chat. If you want to continue the conversation and you want us to walk you through our tool, how to use it and so on, or whatever you need.
Great, thank you. And we're also developing a hydro school to teach about hydroelectric
Cool.
and plumber, with the Coeur d'Alene Tribe.
Cool. Yeah, please, reach out, because we do a lot of outreach too. There, in addition, not just this project, but all of our water power, all of the projects within the water power portfolio. So we're here to help. Mucun and I are also in another project for non-power dams retrofits, where we're looking at similar stuff of cover development with renewables and so on. So there is more work going on. So if you're interested in talking more, we're happy to help.
Thank you.
You're welcome.
Thank you.
All right, I think we are over on time. So if you have questions, again, feel free to send those over to Juan or Mucun via their email in the chat. And I'll also be sending out, an overall email to everyone with details and links and everything to what was mentioned in today's presentation. So thank you, Mucun and Juan, and thanks everyone for joining.
Yeah, thank you, everyone. Bye.
Thanks, everyone. Bye.